Rational Science. Got a raspy voice, just coming out of a cold. Also have erysipelas, which is a bacteria that attacks usually the lower part of your leg. This is what it looks like today on me. You can see I'm turning into a crocodile. My scales are falling off. So, yeah, I'm not in great shape, but the show must go on. The lecture must go on. And I've got a raspy voice. I have no idea why. I've tried everything, even a shot of whiskey. Can't clear my voice. So I'm going to do the best possible today with what I've got. Okay? I just hope I don't have to go to the hospital this week to get some intravenous penicillin. That usually works with my leg. And yeah, I'm getting better, but very, very slowly. Anyways, let's move on to the subject matter of today. And we're going to start with this, fellows. Someone that everybody, or most people know, it's King Arthur. King Arthur and the Knights of the Round Table. I think most of you heard about him, right? And there's a lot of stories on these fellows. That has to do with chivalry and good government, governed by the people and for the people, that kind of thing. The good king who cares about his people, who cares about progress, etc. And so many stories have developed over the centuries on King Arthur. And one of those stories that is very much attached to King Arthur is this golden thing you see in the center, glowing. Glowing means it's holy. What you have is that chalice, right? It's a cup. And as you can see, it's gold. It's probably imagined as being studded with stones such as emeralds and rubies and pearls and whatever. And one of the things here is that this story has been embellished over the centuries. And people are now looking for that chalice, that cup. Supposedly it was a cup from which Jesus, at least one of the stories is that Jesus drank from that cup on his Last Supper. Another of the stories is that Joseph Arimathea, the guy who buried Jesus, he pulled some blood in that cup, and so it's kind of like a holy cup. The funny thing about it all is that nobody knows really what that chalice, what the Grail is. They're looking for this Holy Grail buried somewhere. They said it was buried in southern England. Then others say it's in Spain. Some say it's in France. Others say it never left a promised land, etc. So there's many stories, many myths about this. Everybody's got their own version. But the funny thing is nobody knows what a Grail is. And the original one, it was a plate. The original story. After that, they turn it into a cup. Others say it's a cloth, a piece of cloth like the Shroud of Turin. And others say it's a stone. So we have all these grails out there, okay, different grails. And since the story has been embellished over the centuries, and today we moved away from manufacturing into services and more abstractions, the famous Grail has become, when you talk about the Holy Grail, you're talking about like a dream, an idea, maybe an unreachable one, or one that's very far away, and you're going to try to get there. And the fun or the real good part of it is the trip, the road map, right? And not so much finding it, So those are the notions we have today, but see, these people now have converted this Grail into this abstraction. And so here's the million-dollar question for you. You have mathematical physics. What is the Holy Grail of mathematical physics? Specifically, are we talking about a physical object that they're seeking? Like the mediator of gravity, the mediator of magnetism, the mediator of electricity or whatever? Or are we talking about an equation, an abstraction that once you find it, I guess, you can encapsulate encapsulate all equations that ever invented by man or discovered by man. So which one is it? Which one is the goal of mathematical physics? Well, in physics, we have no problem answering the question, okay? Why? Because you have this, you have, we start with the fact that you can't do physics without an object. So our holy grail of rational physics, of genuine physicists, right, is to find the physical objects, not equations, okay? We can't do physics without an object. And this is one of the things that the mathematicians never learn, because they're always looking for these abstractions, these equations that they're seeking. And so when you talk to them about objects, they have no clue what you're talking about. And they say, oh, that's philosophy. They dismiss it. It's not part of physics. And so we have a problem because we don't know what physics is. Is physics about equations? Is that the holy grail of physics? Or is physics about finding the objects that serve as mediators for phenomena that we still cannot explain, such as gravity and, electricity and magnetism? And so which one is it? And the mathematicians, obviously, they're not into objects, they're not into things, so they always go in the opposite direction. They say, look, we're looking for equations. And so we're not communicating, because when people go to a so-called physicist, a mathematical physicist, the first thing they ask is, what is gravity? Meaning, please explain gravity in a way that I can understand it. What's the mechanism of gravity? How do you do gravity? And these people immediately start coming out with mathematical concepts. Well, here is a field, and here you have the mass, and here you have the energy. That's not what we're interested in. And obviously that's how they do all of their action at a distance, whether you're doing entanglement or gluon attracting two quarks or gravity. It's all the same. It's all done with concepts. And people think they're getting an explanation of a mechanism, a physical interpretation, when they're not. They're getting a mathematical description, which is converted, is insinuated as if it were a physical interpretation, a mechanism. That's where the problem is. And so one of the questions you should ask is, if some of these things that I'm going to show next, they belong to physics or to philosophy or to whatever other discipline, okay? Here you have good old Felix, and he swirls around a horseshoe and throws it through a window, breaks the window. So I ask you, how did the window break? So what are you going to tell me? You're going to say, well, a horseshoe went through the window, period. That's it. That's how you would tell the judge. Judge asks you, how did the window break? You say, well, a horseshoe went through the window. We're done. A mathematician says, well, we had this mass, and it had so much energy, or went with so much energy with a force. Broke the window because the window had was very thin, or could not withstand the hit, the strike. But that's not what a judge would accept as a physical interpretation. Physical interpretation, what you see there, the horseshoe going through a window. Everybody can understand that. It's baby stuff. It's kid stuff. Okay, that's what the type of answer people want for gravity. Like, just tell me, what caused gravity. Don't tell me about mass. Don't tell me about energy. Don't tell me about fields or time or the velocity of light. We don't care about all that nonsense. It's got nothing to do with the question that we're asking. We're asking, why does this fall to the floor? That's what we want to understand. What causes it? And these people say, well, that's not physics. That's philosophy, or who knows what. Is that philosophy? Now imagine this now here, okay? Here we have the same situation, but we don't see what caused the breakage of the window. We see that Felix, does some magic motions there. Suddenly, the window breaks by art of magic, by action at a distance. It's like the voodoo doll. You pinch the doll here, and the guy feels the pain over there. And here, Felix is swirling his hands around, doing some kind of hocus pocus, and suddenly the window breaks. So now if someone asks you, the judge asks you, well, how did the window break? Well, you would know what to answer. You say, well, I don't know. All I saw that he made some kind of movement. Suddenly the window broke. Okay? So what would a mathematician say? Well, again, he would bring in his concepts and he gets away with murder because he says, oh, I can answer that question. Okay, how do you answer it? Well, you have this mass, you see. Where's the mass? Well, mass is kilograms. I mean, what are you going to illustrate? So we have this mass, right? And Felix swung it around with so much energy, right, that he threw it and a force broke the window. And so they answer the question. And people walk away saying, okay, now I know how the window broke. And you haven't understood squat because the guy never answered the question. He did not give you a physical interpretation. He used concepts, mathematical concepts, in lieu of a physical interpretation. Okay? Now here's another situation. Okay? Here we have a cowboy pulling on a donkey. Okay? So we say, well, how did the donkey go from A to B? Well, it was very simple. I mean, the cowboy pulled on a rope that was tied to the donkey's neck and just dragged him over. We all understand that. I mean, we don't need to know any more about force or anything, what moved his elbow, what moved his shoulder. We don't need any of that. We just need to know why or what caused the donkey to move towards the cowboy from A to B. Okay? Now, imagine that you don't see the rope. Again, here you have the situation without a rope. Okay? And the question is now how did the donkey go from A to B? How did he approach the cowboy? And you would not know. You would not, because you can't see the mediator. That's the only reason you cannot answer the question. You don't know what's there. I mean, maybe he's pulling on a wire. Maybe maybe the donkey's being pushed from behind by the wind. I mean, we don't know. We don't have it. We don't have enough information in that picture. And again, a mathematician would say, well, we don't care about the mediator. Okay, we don't care about that. We just say the donkey has so much mass, and there was a force, whatever that is, and pushed him with so much energy that he went forward towards the cowboy. So he would explain it in those terms when he hasn't explained squat. We have no idea what the cause of this phenomena was. Okay? And this is where the mathematicians get away with murder, when they introduce their mathematical concepts in lieu of objects, giving you the misleading idea that they answered the question when they did not. Okay? Final one, and again, the question for you, if any of these has to do with physics, are these questions of physics? If not physics, not a physicist, who's got to answer these questions? Who answers these types of physical interpretation questions, if not a physicist? Okay, that's what you got to figure out. So here you have a pulley, right, and pulling up a box that's tied to a rope that's wound around a pulley. Okay, we all understand it. How did the box go from A to B? How did it go upwards? Very simple. Something pulled on the rope, whatever it is, a machine, a hand, whatever, and it was wound around the pulley, and the box went upwards. We need no more than that. In fact, we can show the movie to a judge, to a jury, and they would understand how the box went up, right? Now, what happens when you remove the rope? Now we're into trouble, right? Because now we don't know. It looks like magic now, right? And the only difference between the two scenarios is here you can't see the rope. That's the only difference. And so the question is, again, a mathematician would use words such as energy, force, and mass to explain, give you a physical interpretation, as they call it, when they did no such thing. All they did was, give you a description, a mathematical description, in lieu of a physical interpretation. And that's where the problem is, primarily in so-called mathematical physics today, which they equate with science. They're saying all this happened. Why? Because we have all these concepts that they invented: field, mass, time, energy. And that's what they use to explain, supposedly, all these physical phenomena. Here you have an example, good example here. Stephen Hawking. You know who Stephen Hawking was? Well, he was a guy who was a guru in mathematical physics. Okay, And this is how he explains gravity. And he got this from Einstein, obviously, not from himself, but he kind of summarized it here. Okay, you can see it. Says, gravity is not a force like the other forces, but is a consequence of the fact that space-time is not flat, as had been previously assumed. Well, I don't know about flat space-time. It was assumed by whom? It could be assumed by the mathematicians, not by rational individuals. It is curved or warped by the distribution of mass and energy in it. Bodies like the Earth are not made to move on curved orbits by a force called gravity. Instead, they follow the nearest thing to a straight path in a curved space. The mass of the Sun curves space-time in such a way that although the Earth follows a straight path in four-dimensional space-time, it appears to us to move along a circular orbit in three-dimensional space. Well, the problem here, he hasn't explained absolutely anything. Okay? All he's saying is we have these number lines, which the mathematicians call dimensions, three-dimensional space. No, that's not what you're staring at. You're staring at number lines, which they forgot to put the numbers on. That's all. This is Rene Descartes' Cartesian coordinates, his irrational Cartesian coordinates. And they're irrational first because they're not coordinates, they're just number lines. And the second part is he puts direction to them. He puts a little arrow at the end of each line, which is totally irrational. It has nothing to do with mathematics or with physics. The direction belongs to physics, exclusively to physics. It's a qualitative concept. You don't have direction in math. You can't put direction in an equation. Okay, so what they have is numbers, and the numbers have no rectilinearity to them. One number does not follow another, like 1, 2, 3, 4, 5 like one right after another. Now you can put the number 2 behind you, the 3 in front of you. You can put them any way you want. Numbers don't have location, so it's irrational to put them on a number line. Okay, but that's what they do. They put them on a number line, then they get rid of the numbers, and they think they're dealing with what? Dimensions? Coordinates? No, they're dealing with number lines. That's what that is. And time is a number line. Okay, time is only a number. It's not a dimension. It's not a coordinate. It's not a vector. It's a number line. Okay, it has no perpendicularity to anything, which is what dimensions have, and coordinates and vectors, right? And it has magnitudes, has numbers, which dimensions, coordinates, and vectors don't have. And so he's saying that he's going to bend these number lines. And because he bends the number lines, which is already an irrational notion, the Earth finds a wall behind it. It's caught in this depression, and it can't leave the bowl, so to speak, the roulette. And so it swings around forever. That's the notion they have of gravity. And it's turned around. What he's saying, look, the sun weighs down the number lines, right? And that's gravity. It should be the other way around. If number lines bend and force the sun downwards, then you would say, look, the cause of gravity is the bending of number lines. But here he's saying that gravity is actually the pushing down of the mass of the sun on, the number lines. So we still don't know why the sun is pushing downwards. Is it maybe Newton's force that's pulling it downwards? Is it gravity? They haven't answered the question. And again, you can see they get away with murder because they use concepts such as number lines. They turn them into physical objects, which they illustrate, as you see there, as a fishnet, as a canvas. And they say, see, we can explain gravity when they haven't explained squat. That's not an explanation of gravity, what you see there. Okay, we started looking at a fellow because of this prediction thing, and his name popped up. I don't know who he is. I know very little about him. I just pulled out a couple pieces of data. I still don't know who he is. His name is John Ellis, supposedly a mathematician, some guru out there in England, merry old England. And it says here that he's the author of 1,000 scientific papers. The sum of citation is above 120,000. My God, he must be a genius. It says Aspire's survey ranked him as the second most cited theoretical mathematician. Okay? Research interests focus on the what? Phenomenological aspects of particle physics. Phenomenological Phenomenological. What is phenomenology? Phenomenology. What is that nonsense? Okay, and here we have a little definition. It says phenomenology, the application of what? Theoretical physics, mathematics, right? To experimental data by making quantitative predictions. Predictions based upon known theories. Phenomenology stands in contrast with experimentation in the scientific method, meaning the mathematical method, right? In which the goal of the experiment is to test a scientific hypothesis instead of making predictions. Okay, so phenomenology has to do with predictions, whereas experiment has to do with, proving the hypothesis, as they call it, whatever that nonsense means in mathematics. Okay, so there we have it. That's what this fellow does. So what kind of things did this guy discover? What did he predict? Well, he calculated the Higgs decay into Z photons. He estimated the direct CP violation contribution to rare neutral kaon decays. Predicted the mass of the bottom quark. I guess that's about sex. You got the top and the bottom quark, I guess. I don't know. Showed that the lightest supersymmetric particle is a natural dark matter candidate. Now, that was interesting because dark matter is supposed to be the heaviest thing imaginable. And he said the lightest supersymmetric particle is the dark matter, okay? Showed that radiative corrections to the mass of the lightest Higgs boson in minimal supersymmetric models increase that mass beyond the reach of the large electron-positron collider. Okay, so he did a lot of work on particles. He did a lot of equations on particles, and I guess that's what he dedicated his entire life to. He's close to his 80s. And what's funny about that is that all his work was in vain. It was wiped out in one swoop. Okay. And here you have Mr. Rowelli. He's going to tell us about it. He says there are no such thing as particles in quantum mechanics. Okay, did you hear right? I mean, first you have to remember that Niels Bohr and Rutherford, all these people in the 1915, 1920 time frame, thereabouts, they came up with quantum and said quantum is a particle theory, the bundle of energy, a little packet of energy. That's what it was all about, whatever energy is, right? But you imagined a ball, a little tight ball of energy. And of course, energy is a mathematical concept, so you can't have a ball of a mathematical concept. But they always illustrated with balls, the beads, the electron bead, the proton bowling ball, right? And that's how the way it's always been illustrated. But this fellow now tells us that there's no such thing as particles in quantum mechanics. Listen to him. Don't listen to me. Listen to him, right? Here it goes. Listen carefully.
Now, if you look where the particle is, if you try to pinpoint the particle, which is a vacuum state, you don't find it zero. There's a probability you find here, you find it there, because that's a spread, the quantum spread of the state. So it's true that if you look, you find it somewhere. Then you look again, you find it somewhere else. Then you look again, you find it somewhere else. Even if you try not to disturb too much, which is hard, you have this spread, okay? But this doesn't mean that there's a jumping particle there. There's a state which doesn't move. The source of the confusion is that we're not talking about particles. We're talking about quantum objects, which are not particles. So a quantum space-time is not a discrete space-time. It's a quantum space-time. To say that a quantum space-time is a discrete space-time is the same misunderstanding as saying that a quantum particle is a particle that dances here and there.
Okay, so no such thing as particles in quantum mechanics. In fact, they came up with quantum field theory, which is a contradiction in terms. And with that, they got rid of the quantum particle forever. Okay, what is quantum field theory? Well, quantum means a little discrete packet of whatever, a little ball. Okay, that's the notion at least. It's not that because, again, you can't have a packet of numbers or values of magnitudes or whatever. But they imagine it and they illustrate it with little balls, right? And you look at the standard model, they're all little balls, right? And on the other hand, the field is something extended, extends all the way to the edge of space-time. So they have the quantum field, they have the discrete extended, which is a contradiction in terms. And they had to introduce the field because they wanted to reconcile quantum with relativity. And relativity is a field theory, so how do you do it unless you somehow incorporate the field within quantum mechanics? And that's what the string theorists are trying to do even to this day, trying to see if they can merge quantum with relativity by, I don't know, talking about fields. And so the quantum is dead. The quantum is no longer there. In fact, you have this fellow, Arvin Ash, and he tells it to us. He says, look, an excitation in the electromagnetic field is the photon. So you have a little vibration there of the field, and you got this peninsula, not a discrete island, but this peninsula known as a photon. What is a graviton? Well, it's an excitation. The gravitational field would be the graviton, right? So we have all these little bumps, these little vibrations, these little cones, these little peninsulas sticking out of the ocean. And I don't know if they gained their independence, but because, otherwise they wouldn't be vibrating, I guess. They wouldn't be vibrating fields anymore. So I guess they're stuck to their field. They have these little bumps sticking out. They say that's a particle. That's what they call a particle, a local vibration of the field. Well, this is great. I mean, that they finally got rid of quantum mechanics, of the quantum. But we have a problem with reconciling what Arvin Ash said with this, with the model of the atom proposed originally by Rutherford and Bohr, which is this nonsense about a little bead rolling around a nucleus. They modified this over the years, but not significantly. All they said, look, it doesn't really orbit in a perfect circle like a planet. Okay, no problem. That's big. That's nonsense. That's petty modification. What they have is the electron. They continue treating it as a bead that is somewhere around the nucleus. That's all they're saying. And this bead can occupy different energy levels or orbitals, right? Which is those circles that you see there. And nothing has really changed. This is the quantum atom. And how do you reconcile this discrete bead with what Arvin Ash just said, which is the vibration of a field that extends all the way to the edge of space-time, and the bead, that little bead, that blue bead that's going around, is nothing but a local vibration of the field. How do you reconcile these two models? They have nothing in common. Okay, there's no way you can even imagine this. You can't picture this. You can't make a mental image of it to get your theory across to rational people. And so, yeah, we have a problem because today we have all these abstractions that they've introduced. And so you wonder if these people are chasing the wrong holy grail. Are they going in the direction of physical entities, real ones that you can picture? And the answer is no, they're not going in that direction. They're going in the direction of more and more equations, unnecessary equations, irrational equations, because they bear no relevance to reality. They have nothing to do with reality. And so they're all going out looking for these equations. They're looking for the grand equation, grand unified theory, or a theory of everything, or whatever they're looking for out there. Some have given up hope. Others continue to search. And they're looking for equations. And you're saying, look, I don't care about your stupid equations. I want to know how this universe works. Tell me how the micro world works. Tell me how the macro world works. And they can't do either one. Because in the macro world, they're going to introduce their space-time nonsense, dimensions, which they call dimensions. They're number lines. They're going to bend them. They're going to talk about warping of space-time. And time is a concept, and they're going to warp it. They're going to bend it. What sense does that make? And they tell you that's gravity. That's even worse. So we're stuck with this goal that the mathematicians have, which they're completely on the wrong foot, wrong path. And some people like Hossenfelder and Weinstein, all these people, they realize something is wrong because they kind of painted themselves into a corner. They can't get out. They can't make sense of it anymore. There's nothing more to investigate. What are they going to do? Come up with more particles? And they say in order to come up with more particles, we need bigger colliders, the size of the Earth or the size of the solar system, to smash them and find out what those particles are made out of. And all they're going to do, assuming we could fund that and it's feasible, right? Engineeringly feasible. All they're doing is smashing particles and say, okay, now Johnny is made of 2 or 3 Charlies. So they're just going to give names to the new particles, and they haven't understood anything anyways. We've been doing this for 100 years now. Smashing particles, allegedly smashing particles, and naming the debris. That's all we've been doing. And that's what your tax dollars are paying for these days. Okay, let's move on to predictions, because it's part of the subject matter we just covered, because again, these people talk about doing predictions that they can predict. And again, that's what math can do. Math can predict, because, you know, a simple example I always give, a car runs 50 miles per hour on a constant rate in a straight line. You can predict it's going to be 50 miles away, all else being equal. So you predict it. So what? Is that science? Well, that's what they call science. You know, they say we can predict an eclipse tomorrow, 4 o'clock in the afternoon. You know, the moon goes between the Earth and the sun, and we have an eclipse. So they had 4 o'clock tomorrow, I can predict there's going to be an eclipse. Okay, so what? Is that science? I mean, all you did was describe. You're saying something's going to happen tomorrow. You know, it's like you go to races and your buddy says, your mathematical buddy says, I predict that horse number 1 is going to win this race, 2-horse race. And I'm saying, look, and horse number 2 is much better, much faster. We know this for a fact. So I'm going to bet on horse number 2, because I know horse number 2 is going to win. There's no horse number 1. I predict horse number 1 is going to win. Okay, so each one places his bet. The horse is run, and horse number 2 is beating the crap out of horse number 1. I mean, by a mile. I mean, it's just a fast horse, right? And just about, you know, a few yards before horse number 2 reaches the finish line, your buddy pulls out a gun and shoots him and kills the horse and the jockey. And horse number 1 just gallops in there and wins the race. So he's right. Yeah, he didn't have an explanation before. Now I got an explanation in retrospect. I know why horse number 1 is going to win the race, because he was going to shoot horse number 2, something I did not know what's going to happen. He knew it. Okay. Okay, and this is the same thing with when you have an eclipse. You know, as long as you say there's going to be an eclipse tomorrow at 4 o'clock, you haven't said anything. That's a description. We still don't know why that's going to happen. If you can explain why, you're no longer talking about a prediction. You're no longer talking about the future. Now you're talking about the past. Okay, explanations, we can only explain the past. Means that you're drawing on your memory, you're drawing on your experience of something you've already experienced or read about or know about. So you know that, the moon goes around the earth and gets in front of the sun every now and then. That's when it causes an eclipse. That's the cause. Okay? So if you can explain that, you're talking about your past. You're talking about some experience you've already had with the phenomenon. But as long as you just say tomorrow at 4 o'clock there's going to be an eclipse, we still don't know why. And that's just a prediction. That's just a description. Only when you explain can you talk about the past. And it's no longer a prediction. Now you're talking about explanation. Explain, we can only explain consummated events. Okay? Okay, so what is a prediction? Well, here we have a little definition, typical one from the dictionary, nothing out of the ordinary. Okay? Predict, to declare or tell in advance, to prophecy, to foretell. Okay? Prediction, a statement about what someone thinks will happen in the future. Okay, so again, it's just a description. That's all it is. And, you can have an intelligent guess, right? You can say that's a prediction. You can also have, the owl and the astrologer and, tarot cards or whatever, palm reading, and do something else, and say that you got it from your prediction from somewhere else. I always say that when you go see an astrologer, someone who claims to predict, the future for you and read your palm or whatever, look at the zodiac or whatever. Very simple. Just ask them, please predict when I was born. I mean, if you can't predict something that's already happened, I doubt very much you can predict something that hasn't. Okay? So I always ask them, predict when I was born. Okay, and we have here someone who did suggested that we could conceivably, if we knew where every little atom in the universe was, we could predict, all future events. Okay, here we have, his name was Pierre Laplace, late 18th, beginning of the 19th century. Says, we may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at certain moment would know all forces that set nature in motion and all positions of all items of which nature is composed, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, right, the devil, I guess, or the God, I don't know, nothing would be uncertain, and the future, just like the past, could be present before its eyes. And in a way, this wasn't an original thought. St. Augustine also thought of God as the God of time, like he had the whole block universe in front of him so he could see the future, the past, and tell you everything that happened and will happen just by looking at this thing. Like he was outside of time. God is the God of time, but he's also the God who is outside of time, right? Time does not affect him. In that sense, he's eternal, and so on. Those are the notions that Augustine had. One problem here, we get it from the bot, okay, R2D2, and what does R2D2 tell us? It says, prediction. Future events are inherently unpredictable. Okay, the world is complex and constantly changing, making it difficult to accurately forecast what will happen in the future. Okay, unforeseen events. We have unexpected events like global pandemics or technological breakthroughs can disrupt even the most well-considered predictions. And then he says also you have the human factor, human behavior is unpredictable, so people do things, at the spur of the moment, and obviously, we cannot predict what everybody in the world, at least, will be able to do the next minute, right? So the bot is primarily thinking of living entities, and that's not really what the mathematicians are talking about. What they're talking about is inanimate objects, atoms. Can we predict those, right? Where the atom will be next. Now, remember, you have atoms in your body also, and so if you decide to move left instead of right because of just whim, well, then that atom goes with you. Okay, so you move the atom in the wrong way than it was predicted. So in that sense, yeah, I don't think you can predict, at least atoms belong to living entities. But if we just look at macro objects or atoms out there in space, like the universe, well, I think we can more or less, if we knew the direction which each atom is moving, and we know the location of every atom, I guess Laplace would be correct. We could predict, where it would be next, okay? But what's the issue? The issue is that we have rotten language from the mathematical establishment. And one of those words is predict, but it's not the only one here. Here they are. We have the three misleading words of mathematical physics, and that's predict, observe, and discover. They observe, they can see something, right? Something happened. They don't understand squat. They saw something happen. They say, oh, let's try to explain that. And so they do what is known as a prediction in the religion of mathematical physics. What is a prediction? Well, prediction is really an assumption, and they call that a prediction. And then they do an explanation based on that assumption. They call that whole package a prediction. And when they go out there and they think they saw what they predicted, they say, oh, we discovered it, we found it, we proved it. Now it's a fact. Okay, no longer a theory. That's more or less how it's handled. So let me summarize it here, okay? Let me get rid of this here. So we have this discovering, predicting, and observing. That's the language that the mathematicians use when they really mean assuming and explaining. So they use this misleading language. They say, "Oh, we predict, we observed, we discovered," and they're not talking about anything. Why do they use that language? They have to reinforce the fact that They're not just making an assumption. They're not just theorizing like, well, that's just a theory. No, no. They want to show you that they know, that they've proven, that they've got evidence. They got not only the equation, but they got the experiment to prove it. So they want to show you that they really know, that they really got it down packed. Okay? And so they have to do a prediction. And part of that predicting thing is the equation. You need to have that equation because people look at, mathematicians, other colleagues, right? They look at the equation and says, okay, this equation says that this is what's going to happen if we do this, this, and that. We fill it with so many variables, right? And so they say, okay, let's see if this is true. And they go to the lab or to the field or whatever, and they run a test. Now they're observing, they're looking, they're saying, oh, we measure, right? And that's when they discover. They say, oh, we proved it. We discovered. And what they're really saying is we're making an assumption. We're making an assumption, for example, that we're dealing with particles. That's a big assumption. Quantum mechanics only makes one assumption. That's that they're dealing with particles. It's the particle hypothesis. And so no matter what, they always deal with particles. And everything is explained with particles. So guess what? Everything turns out to be particles. Even some of the equipment that they use, the photomultipliers, photosensitometers, and so on, they're built to count blips as particles. So it's all particles, no matter what. And so it's not surprising that all the theories have particles in them, partly because they can model a particle, the location of a particle, the mass, the charge, whatever, with equations. They have a single point. And so this point, this location here, this thingy that we can't see that we think is a particle, it's got this charge, this mass, it's got this spin, all the good stuff. So they assign all these properties to that location, to that point, which they assume is a particle. And when you ask them, what's a particle? Well, that's when Carlo Rovelli tells you there are no particles in quantum mechanics. And people like Arvin Ash and Sean Carroll, they tell, well, they're all fields, vibrational fields, whatever that means, so you get all these runarounds. And they talk about proving and knowing. Why? Because they're really trying to persuade, convince you that they're right, that they're correct, and that you are a dumbass, that you don't know anything. They try to convert you, and a lot of people just get swayed and follow the buffalo herd, and they get recruited. They form part of the congregation. And then you have to put up with them coming over here. And a lot of these people, they come in here and they start talking about, immediately they start talking about mass and energy and, all these words that they use, force and time. A fellow was talking the other day about currents. He says the current in the vortex. And I said, okay, what physical object is in the vortex, is causing this vortex? What physical object is causing the current of all this material that you're saying is being taken by the current? He talked about the flow as if a flow is a physical object. And of course, he couldn't answer the question. He ran away with the tail between his legs because he has no answer. They're all talking about these abstractions that were fed to them by the mathematicians in high school and in college, and that's all they talk about. And instead of understanding that you can't do physics without an object, you absolutely need an object. Period. We're done. You can't do. Any rational person, right, sees this happening, right? We're going to do a little magic trick here. We call it gravity, right? We let go of this and it falls to the ground. And it always falls to the ground. And so you say, well, nothing seems to be in contact with this thingy. So all we have is the Earth and this. That's the whole system. You can have an astronaut and the Earth. The astronaut falls to Earth. The system is astronaut and Earth. That's it. Why does he fall to Earth? Why does that fall to the center of the Earth? And immediately they start moving into, well, the mass, the density, the volume. You start talking about math. No, I don't care about your stupid math. Keep it to yourself. I need to know what physical entity brought it down. And any rational individual, if you're a rational individual, you know that something is in contact with this thing for it to come down. There is no such thing as action at a distance, because action at a distance is the scientific term for witchcraft and black magic. It's voodoo science. You know, you pinch the doll and the other guy gets hurt. Yeah, by what mechanism? How do you connect this event, this phenomenon, with that event over there? And to say that, look, every time I pinch the doll whenever I want, this guy feels the pain everywhere in his body. And there's no connection between the doll and the person? There's nothing there? And a lot of people actually believe this nonsense that, all these concepts flow through the air. And that's when the mathematicians come in and they say, well, it's the energy, it's the mass, it's the charge. They bring all these concepts and treat them as physical objects. People think they got an explanation when they have not. Okay, that's where the problem is. Okay, so let's go through some of the predictions of the mathematical establishment and find out how they predicted these things, how they came about, how they were observed, how they were discovered. Today we treat them as done facts. It's unchallengeable. And here you see some of these examples. Here's spin, okay? How did we come up with spin? Well, here's a brief history of spin, right? You have 1922, we have the Stern-Gerlach experiment. They observed spin. They observed something they could not explain. They tried their best to explain it. And they said, oh, we discovered it. Or we found this event, this phenomenon. That was the observation, okay, part. Okay, 1924, Pauli and others apparently prophesied spin and said, the electron and some of the particles have spin, whatever that is, okay? And 1925, these other two fellows also, they prophesied again, I guess, By 1927, these people, they ran the Stern-Gerlach experiment again, whatever it is, we don't care, okay? And they discovered spin. They were able to explain spin to the satisfaction of the mathematical community, and that's when spin became a part of quantum mechanics, okay? Now, the funny thing is spin is not spin, what you see there, a little ball turning. So what is spin? Well, let's look up the definition. Let's see what spin is, okay? And here you see it. Spin, an intrinsic quantized form of angular momentum. Quantized form of angular momentum? What do you mean quantized? They're saying it's discrete of angular momentum. So you have a little angular momentum, a chunk of it, a little piece of it, possessed by elementary particles that is not a result of physical rotation. So we're talking about angular momentum with no momentum. There's nothing moving, okay? So see if you can try to understand this, right? They're talking about a movie, but they're saying, look, we're taking a snapshot of a portion of it, and we're going to call that spin. You look at a top, you spin it. Okay, we can film it. We know what spin is, right? Spinning of a top. That's not what spin is in the religion of quantum mechanics. So what is it? While the term spin suggests a physical rotation, it's important to note that quantum spin is not a classical spinning ball. Classical means rational. Whenever you talk about quantum mechanics, they're talking about irrationality. That's what it's called. But they like to talk classical and quantum instead of rational and irrational. By rational, I mean that they try to rationalize it with balls. When quantum mechanics came in there, they forgot about rationality altogether, and they forgot about balls. The famous quantum is not a ball, okay? Not a ball of numbers, right? It's a fundamental property of a particle itself, and the idea of a particle physically rotating at the speed of light is not a viable explanation. In quantum mechanics, angular momentum, including spin, is not continuous, but comes in discrete quantized units. What the hell? What are you talking about? What is it? Please illustrate the stupid thing you just said. Meaning can only take on specific values. And so the first thing they did, instead of talking about clockwise and counterclockwise spin, right, they began talking about half, one half, negative half, negative one spins, whatever that means. What do you mean negative half spin? What is that? And so spin is related to the magnetic properties of particles. A spinning charged particle generates what? A magnetic dipole moment, which is why electrons can interact with magnetic fields. Okay, whatever that means, because they're saying we have a field. Field is a concept, a bunch of numbers, right? That's all it is. And they say that the electron has this property called spin, and because it has this property called spin, which is a bunch of tiny numbers, half, minus half, 1, etc., right? Just numbers that interact with a magnetic field, which is a bunch of numbers. So we have numbers interacting with numbers. That's all you have so far. That's what they're talking about. The Stern-Gerlach experiment demonstrated the quantization of spin by showing that particles with spin minus half, like electrons, can be deflected by a magnetic field in two distinct directions, corresponding to the spin up or down. Spin up, spin down. Well, I never saw a top spin up or down. They spin sideways typically, horizontally. Okay, but this is the nonsense they put out there. They cannot explain spin. They have no idea what spin is, but it turns out that they predicted it, they observed it, they found it, they discovered it. It's a done deal. We're done. And so the question is, is the electron a particle to begin with? And if it's a zero-dimensional particle, because they say it has no size, or it's below such a size that for all practical purposes, it can be considered to be zero size, no shape, no volume. How can you imagine something like that spinning? And if not the electron, certainly a singularity, in the center of a black hole or at the Big Bang, it's a zero-dimensional nothing, no volume, no shape, no size, no diameter, no radius, no volume, but it's spinning. Yeah, called a Kerr black hole. Kerr singularity spins. It's nothing that spins. Great. Okay, here's another prediction to see how they came up with that one. Here you have good old Wolfgang Pauli, Austrian guy, During beta decay, an emitted electron carried less energy than expected, seemingly violating the law of energy conservation. In 1930, Wolfgang Pauli proposed the existence of a new neutral and nerdy massless particle that carried away the missing energy and momentum. Carried away, missing energy. How do you carry away energy? Energy is a concept, a number. That's all it is. What's momentum? Another number. So how do you carry away numbers? I guess on a wheelbarrow, maybe a wagon, I don't know. In 1932, Enrico Fermi dubbed the particle a neutrino, and in 1956, Cowan and Raines conducted an experiment that provided the first direct evidence for the existence of the neutrino. This is how they discovered it. Electron antineutrinos were emitted from a nuclear reactor and found to interact with protons of the water in a nearby tank. So there you see the reaction. You have the antineutrino, which is that little V sub E there, plus the P, which is the proton. That's why it's got the plus sign on top. So these two reacted and created a neutron, which is that N with subscript 0, plus a positron and a positive electron. That's why it's got a positive sign instead of a negative one. And so with this equation, it matched the equation and said, we proved it. We've discovered it. Okay? So now you know how these things come about, how they prove them, how it's discovered, observed first, predicted then, and finally discovered. Okay, here's the neutrino event, and this is what they saw in the bubble chamber. They say, look, we see this line there, and that's a neutrino transformed into a mu meson. Okay, so what are we staring at? Well, you see some curlicues there, and you see some lines. What is all this stuff? Do they know? They think all these are traces of particles. And I got two problems with that, especially the ones that are the curlicues there, the spiraling ones. First of all, these particles are traveling close to the speed of light. And for them to turn a corner, such a sharp corner at the speed of light, hey man, I'd like to see you try it with a car, I don't think you could do that. I don't think the poor little photon can do that. And what they do is they just have these squirting little curlicues, and the first problem is that the speed. I don't think you could produce those curlicues at the speed of light. That's the first one. Okay? The second one is that you see the whole curlicue. I would love to see a picture of each one of the dots that make up those curlicues. In other words, they took a picture of a movie. They showed me the whole movie. They showed me the whole curlicue, the whole trace, the whole itinerary in a single snapshot or image or whatever, however they created this with computers, right? And you say, well, can I see just one dot there? Can I see just one particle? For example, the proton path or the neutrino path or whatever, right? Whatever you want to show me, no problem. You want to see a muon, no problem. A pion, no problem. Electron, no biggie. Just show me one electron, one muon, then show me the next one, and the next one so that I'll build a trace myself, okay? Just show me each dot that makes that trace. And of course, they always show you the curlicues. They show you these curves, and they say, well, that's a trace of a particle. Well, again, speed of light, very hard to do that. I'd say it's impossible, and that's the first issue. And the second one is, why can't we see the single particle instead of the whole trace? Okay, so again, the question is whether any of this resembles what really they think is happening in there. And again, I like to say, imagine you're skipping rope, right? And you painted the wall. You painted all the wall red. And now you give it a whack with your rope. Well, you get this curve. Did we make the curve by throwing little ping pong balls all along the curve? No, we did it with a single whack of the rope, right? And I'm saying that's what we're showing there. What these people are showing is that we have this, we shook the bee's nest, and because you shake them, it shakes all the things that are connected to that at that region. And that's what the gases in the bubble chamber are detecting when they take a snapshot or however they construct these images, usually computerized, obviously. It's not that they're looking at a trace. They're looking at a single shot of a vibration of all these things that are connected to whatever's shaking in there. And I'll show that in a minute. Okay, so here's another prediction, and this was made by a fellow named Paul Dirac. He predicts the positron. And I call it the suppositron because, again, he's not predicting anything. He's making an assumption. He's supposing. Okay, and that's why it's a suppositron, because he's supposing that he's talking about a little particle. That's where it starts. He created the Dirac Sea with all this nonsense. But the point is, he said, look, there's a positive electron. He predicted it. No, he didn't predict it. He's making an assumption that not only are there negative electrons, but there are positive electrons, which he calls a positron. Okay? So again, the fact that they're using this language, that they predict. Why? Because they want to show that, like astrologers in the past, that they know. They've got the inside story, the inside ear from God. So they know. That's why they talk about predictions, not assumptions. Because they said, well, it's an assumption. They say, I don't care about your stupid assumption. But if you say, I predict, let's prove it. Let's find out if it's true. And turns out, it always turns out to be true. Always, predictions always come true. And here's how it became true. Here we have Carl Anderson, and a couple years later, 1932, and that's his suppositron. And what is it? It's again a little line, a little streak, trough, a trench, channel. One of the problems with that, again, the first one is that those curves don't happen at the speed of light. You can't turn corners at the speed of light. Okay, you would think that anything traveling at the speed of light would have a very long curve and not a very sharp curve like you see there in a wafer this size. Okay, that's the first issue. The second one is that that's not a continuous trough. It's not a channel in the ground. You took your excavator and made a little channel on the dirt. A continuous one. No, if you look at that carefully, you'll see some spots that have no potholes in it. So it's like the particle went up and down. It's a jumping bean. So it made a hole here, jumped up, went down, made another hole, went up, down. And assuming that's true, then what made the jumping bean go up? What made it come down? I mean, this thing goes bing, 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 up and down because there's no direct trough. So how did they come up with this? Well, they said if it would have gone to the right, it would have been an electron because the magnets were set up that way. But since it went to the left, well, it's a positron, a positive electron. And that's how they proved it. Get my Nobel, forget about everything else. Okay? And that's how they did it. Anderson got his Nobel for proving, discovering the positron, suppositron. Here's another prediction, Murray Gell-Mann, and he predicted quarks. And I talked about that a little bit the other day, and he comes through all this stuff, does his math, and you don't have to read all that. You can read it later, but let me just synthesize it like I did the other day. Okay, here it is, okay, which is easier to understand. We have these charge accounts, the Visas and the MasterCards, okay? Visa's worth 2/3, plus 2/3. MasterCard, you have a negative balance, you got a negative 1/3. So let's say you have $66, 33, two 2/3, right? You have two Visas there, right? Two charges. Each one is $66. You got $133. But it turns out in your MasterCard, you have a negative 33, so you have 133 minus 33, that gives you 1. That's the charge on the electron, charge on the proton, right? Which Millikan says is unbreakable. Well, they had to break it down into thirds in order to show the scheme. It's just a mathematical scheme. It's an accounting scheme. That's all it is. And they had to explain why the neutron has no charge. So they said, well, now if you take two MasterCards and one Visa, right? We have two 1/3, negative 1/3. That's a negative 2/3. And what was the Visa? A positive 2/3, negative 2/3, plus 2/3. That's 0. That's why the neutron has no charge, because it's got these quarks. I'm sorry, these charge cards. These quarks in there that have partial charges. That's how they had to break it up into charges. Otherwise, they couldn't explain the scheme. So are there quarks? Are there gluons inside the proton and the neutron? Absolutely not. It's just an accounting procedure to explain why the neutron is chargeless and the proton has a charge of 1. That's all it was. And that's how this got into the literature, right? This is how they proved it, okay? And that's how good old Gell-Mann won his Nobel Prize, right? Because he was able to come up with this scheme, right? Okay, so did they ever prove it? Well, here you have one proof, which was by the BNL, the Brookhaven National Labs. And what they did, they smashed two gold ions, right? They smashed them, and that's what you get, all these particles supposedly tracing out of ground zero. Okay, so they're all coming out of that center, rushing away, right? This is a hand grenade thrown in the center, and all the debris is moving outwards. So they're saying that each one of those lines is a trace of a particle. That's what they're saying, okay? And again, you can see that this is always based on the assumption that we're dealing with particles. That's what they're doing. They're saying, look, we've got particles, we smash these two particles, we got all this debris. What else could it be if not gluons and quarks, which have already been predicted by Mr. Gell-Mann? That's how they did it. Well, if you look at this, it looks more like the model of the rope atom. Here it is. Okay, that's our model. That's our atom, right? The outer skin, the red ball of yarn, is the electron shell, the electron membrane that encapsulates the proton star. And just imagine for a second that you smash these two of those together, right? Well, I think the effect it would have on the gases inside the chamber would be what you see in the right. For a split second in which the image was made, you would think that, all these lines would somehow cause some effect in the gas, and that's what they imaged, right? That's a proposal. Now, I'm not saying we've proven this. I'm not saying you should believe this. I'm just saying that we have a different explanation for this stuff that they show as the gluon quark particles scattered from the collision of two gold ions. In fact, theirs is irrational because, again, they took a picture of a movie. each one of those is a trace. So you're looking at a movie of each particle moving outwards. And they took a snapshot of the movie. I would love to see each little dot that makes up each one of those lines. Then we would know it's a particle that's leaving ground zero. Right now, we can't affirm that because all we see is that lines. And they're saying those lines are traces. Prove it. Prove it that they're traces. And the way you're going to prove it is showing me the intermediate particles, at different locations along each one of those lines. Then you can prove it. But they never do. They say, oh, these are traces. We proved it. Give us our Nobel Prize. See? And so at least we have an explanation for it that is different. We're not saying you should believe it. We're just saying we have a different explanation. And ours is a little more rational because we're talking about a snapshot. A single image, however it's created. We're not talking about traces. Okay, Gell-Mann didn't stop there. He also, again, predicted the gluons, and here it is. He predicted in 1962, but gave it little thought after that, until 1964, when he had to incorporate it into scheme, of the quarks. He said, well, what pulls the quarks together? Well, it's those springs, bed springs. That's what they are. And they look like that, like the gluon bed spring at the bottom. That's what it is. They hold the gluons together. The quarks together so that the quarks don't fly out of the ball. And it turns out that ball, that dotted line that you see all around, that's also put in by hand. I mean, how do you make a ball with 3 balls? I challenge you to do that. Just take any 3 balls. You can take a ping pong ball, bowling ball, or all 3 balls of the same size and make a circle with it. And I don't think you can. So that circle, that encapsulating ball, is put in there by hand. And they say, well, you understand why the quarks don't fly out. Yeah, because it's got this ball on the outside preventing the quarks from flying out. And it's got the gluon springs holding them together, so we all understand why the quarks don't fly out of the protons or neutrons. Of course. No kidding. I mean, we can see it, right? But they're all put in by hand, And here's when they discovered it. I think it was 1979. The 3-jet event in Tasso detector at Dessau in Germany. 2 quarks produced in an electron-positron collision emit a gluon. There you see the little dotted lines. Each of the particles turn into a jet of particles. So we have fireworks. A particle turns into more particles, which turns into more particles. And they say, what else could it be except the gluons and the quarks? Which were predicted by Gell-Mann, for which he won a Nobel Prize, so we can't tell him to return his Nobel Prize. Okay, what's the problem? Well, we have a little bit of problem with a gluon because here it is, that's what it looks like, all those bed springs again. And so what's the problem with that? Well, you don't see it in the standard model. Standard model, where do you see? I don't see a spring, a bed spring. I see a ball. In fact, all the standard model is just balls, little balls, which Carlo Rovelli tells us, there are no such thing as particles in quantum mechanics, meaning balls, right? They're all, what do you call them? Quantum objects, whatever those are. And who was it? Arvin Ash tells us, well, they're fields, vibration of fields, peninsulas, not discrete islands. So we don't know what a gluon is. We don't know what a quark is, but they proved it, their existence. They know that they're there, And here's one thing that they explain with that. It says the gluon tube. They have these tubes, right? And they stretch them. Oh. And they say, look, it's like a bed spring, like a rubber band. The more you pull on it, the stronger you got to pull, right? At some point it breaks because the energy necessary to do that is less than the energy to fly out of there, And so they explain it again with energy, with charge, with all these color and flavor and charm and whatever. They put all these parameters that they created. They don't know what they are. So they weren't satisfied with charge. They had to invent all these other little subcategories and also subcategories for charge, like 1/3 charge for the quark and so on. So again, they just keep moving the goalposts. That's all they've done. They just create names for stuff that they don't understand. And whenever you question that, they say, oh, Bill, you're doing word salad. You're doing philosophy. Go to the philosophers, other side of campus. Okay? Okay, does it stop at quantum? No, we have also relativity problems here. We have here the black hole, how they were detected, predicted first, right? Observed, etc., etc. And here we have brief history of the gloomy black hole, 1783, John Mitchell, celestial objects so massive even light cannot escape. So he already kind of calculated that in his mind, maybe at least, I don't know if he did numbers there, but he said, hey, there could be such a massive object where light cannot even escape from it. Okay? Because again, they thought of light as a little particle that is flying around and says, well, it has so much energy, it needs such and such escape velocity from this big mass, and if it doesn't have enough escape velocity, it cannot come out and come to your eye. And that's why a black hole is black. Okay? 1916, Albert Einstein. Theory of general relativity, a sufficiently massive celestial object could warp space-time. Okay, so he came up with the same notion, more or less. Karl Schwarzschild, same year, he calculates the mass, the size, the volume, right? 1930, Subrahmanyan Chandrasekhar. And what did Chandrasekhar come up with? Well, he says he calculated the radius of a black hole and says it's 0. Let me repeat that because a lot of people haven't heard. The diameter, the radius of a black hole is 0. And it's still, a lot of people have problems with that in their minds. They say, well, what are you saying, Bill? It's 0, meaning there's nothing there. The singularity, which is the heart of black hole, black hole is a star that collapses upon itself through gravitational collapse, right? And it just crunches everything so much that it turns out that crunches all matter out of existence, and you end up with what is known as a singularity. And there's two versions of that. One is that it's a hole in space-time, which you can go to another universe. Another one is that it's just a zero-dimensional object, the center of the black hole, whatever that is. Okay, and so, it squashes so much that there's nothing there. And what Chandrasekhar came up with is, he says, he proved that the radius is 0. And he got the 1983 Nobel Prize for proving mathematically that the radius of a black hole is 0. Okay, for those of you who think of something else, all black holes have the same size. They're all 0-size singularities surrounded by a concept, which has no size whatsoever, right, known as an event horizon. So we have a concept surrounded by another concept. We have a nothing surrounded by a nothing. And what's the issue? The issue is that it also has no mass, because mass is the quantity of matter, and a black hole crushes all matter out of existence. So we have no size, no shape, no nothing, no volume, no radius, no diameter, and no mass, because all matter has been crushed out of existence, and mass is the quantity of matter. Therefore, we have absolutely nothing. That's the definition of a black hole. All black holes have the same size. All black holes have the same mass. They're all infinite mass in 0 volume, meaning we are talking about absolutely nothing. But even if we concede the mass, okay, let's concede it. What the hell? Let's concede mass. Okay, mass is kilograms. So we have kilograms here, bunch of them, as many as you want. Just take your pick. How does those kilograms move a star around or flay its skin, flay it alive? How does it pull gases from another star over there? Mass, kilograms. How do you do it? And again, they begin talking about energy and fields and time and the velocity of light and who knows what other nonsense that has nothing to do with the question asked. I want to know physically, how does mass pull, skin, gases from another star, which is thousands of miles, if not, light years away. That's what you get to answer. It's very simple, really. And John Wheeler named it black hole in 1967. 2019, we got that stupid, idiotic picture, which was touted as being a black hole. That's a picture of a black hole. Is that what it is? Well, let's make sure first that that's what people said it was. Okay, let's make sure that cover that base. Here's CNN says, first picture of a black hole. Okay, straightforward. That was the title. Okay, that's CNN. Here's TED Talk. Okay, people at TED Talk, says the first ever image of a black hole, and they bring the guy who was in charge of taking that picture. Okay, or the team that took that picture. Okay, so there you have it. Okay, first picture of what? A black hole. Here's another example. Wired says a new snapshot of a black hole reveals its mysterious physics. Says, again, groundbreaking provides clues into how the cosmic phenomenon gobble up matter and so on. But this is a picture of a black hole. Snapshot of a black hole, right? That's what they're saying. Okay, and this is all around the same time. Here's the EHT, the Event Horizon Telescope people who took the picture. Again, they say, what? What I'm going to release the supermassive black hole in the center of a galaxy. Okay? So they're saying that picture is a picture of a black hole. So weird, okay? But that's what they all said, and that's what they all say even to this day. So please do not deny it. Okay, so here we have BBC Sky, okay? Night Magazine, how astronomers photograph what? The first image of a black hole. 2019, astronomers released the first image of a black hole, but how was it done? Okay, and what does the image show? Okay, especially that. So what is a black hole? Well, a black hole is an enormous amount of matter compressed into a tiny amount of space. Absolutely not. That's not what a black hole. Black hole is an enormous amount of mass, not matter. All matter has been crushed out of existence. Enormous amount of mass, whatever that is, in a zero space. Zero space. Okay? No shape, no size, no nothing, no radius. Okay? Black hole is not a real hole, no kidding, but a hole in space and time. Okay? So we have a hole in two concepts, especially the concept time. So we got a hole in time. I guess a hole in the second, or who knows what unit, because it's punched a hole in our observable universe. What we're seeing is what? Okay, is a dark region in the very center. Yeah, I see the dark region in the very center. The darkness of the event horizon. No, you cannot see the event horizon because it's too small, according to the same people of mathematical physics. They're saying the black hole, the event horizon, is zero-dimensional because what you have in the center is a zero-dimensional singularity. And how does a singularity produce an event horizon, which is a concept that blocks light or whatever, absorbs matter, whatever? How does a singularity do it? Singularity is a concept. And I said, but surrounding it is an enormous amount of light. Yeah, no kidding. And that comes from the fact that matter is falling into the black hole. It's heating up. It's rotating with the speed of light. And all this is funny because they say that there's nothing that you can do to photograph or make an image of a black hole. And here you have it, okay? Says, black hole is a cosmic body. Absolutely not. There's no body at all. Of extremely intense gravity. Black hole usually cannot be observed directly. No kidding. Yeah, because why? Because it absorbs light, right? And they can be observed by the effects of their enormous gravitational fields on nearby matter. So the picture you see there is not a picture of a black hole. What you're seeing there, in the best of cases, is matter falling into a black hole, right? So we're not taking a picture of a black hole, we're taking picture of a drain, and we're looking at all the garbage that's falling inside the drain. We don't see the drain, the hole of the drain. Okay, so that's where the problem is. These people are lying. These people are misinterpreting or misconstruing what they're looking at. Okay, this is not a black hole. And just in case, just to top it off, to make sure you get it right? Here's Stephen Hawking. Stephen says the following. He says, Chandrasekhar calculated that a co-star of more than about 1.5 times the mass of the sun would not be able to support itself against its own gravity. Okay? Would it collapse to what? Infinite density. What does that mean? Infinite density means zero-dimensional volume. Right? That's infinite. Okay, Eddington was shocked by that implication, and he refused to believe Chandrasekhar's result. Who worked for Eddington? Eddington was the boss. Eddington thought it was simply not possible that a star could collapse to what? A point. What's a point? A location. That's what a point is in the religion of geometry. Okay? Einstein himself wrote a paper in which he claimed that stars would not shrink to what? Zero size. Zero size meaning no volume, no shape, no radius, no diameter, no nothing, no volume, nothing. However, he was awarded the Nobel Prize in 1983 for his earlier work on limiting mass of cold stars. Chandrasekhar had shown that the exclusion principle could not halt the collapse of a star more massive than the Chandrasekhar limit. Okay, so we got it. What is the size of a black hole? Any black hole, whenever they ask you, zero. That's the size of a singularity. And what is the size of an event horizon? Well, if the singularity is absolutely nothing and has no mass, I have no idea what an event horizon is. Event horizon is another concept that they invented, and they call it a ball. They illustrate it as a ball when it's just a concept. It's like, the fireplace. The camp in the fire, right? You have a campfire, and you have this heat. And the moment, the farthest point where you can still feel the heat, well, that's the event horizon of the campfire. So it's a concept. It's the region where you can still feel the heat, after which, you no longer feel the heat. And that's what an event horizon is. It's just a region surrounding a singularity, which is absolutely nothing. And even if we concede mass, we still have no explanation how mass affects a star, which is thousands of miles away. So all that is garbage from the mathematical establishment. None of it makes sense. You can't possibly make sense of any of that. Okay, how about dark matter? The last one here. Okay, how did they come up with that? Well, here's a brief history of dark matter. We have 1933 Zwicky predicts dark matter. Okay, then Rubin, 70s to 78 more or less, because she worked on it several years, measures galaxy rotation curves. And she published some stuff with that with her team, and mathematicians inferred from the data that, that they were looking at invisible mass, something they could not see, but the mass is there because they had no other explanation. Was that a prediction? No, it was known as an assumption. Not a prediction, it's an assumption. They're making an assumption that there's some matter there because they have no other explanation for it, of why the galaxy rotates, the stars on the outside rotate faster than the ones on the inside. So they sprinkle all these kilograms, these red kilograms there on the outside, to make it fit the equation, so that the equation fits observation. Okay? They made it into a tautology, so that whatever's on this side of the equal sign is equal to whatever's on the other side of the equal sign. Why? Because they had to increase this mass in order for the velocity on the outside of one of these stars would be able to overcome the extra radius. That's all they did. So, again, this is just hand waving. That's all it is. Okay? They just had to get their way, and they say, this is the only way we can explain it. We just sprinkle dark matter all over, and we're done. And now they tell the astronomers, go look for it. Okay, so let's look at a summary of all this, okay, and see if we can make sense of that. This is a summary of when they were observed, predicted, and discovered. We have spin, neutrino, positron, quarks, gluons, black hole, and dark matter. The world of the little and the world of the big, okay? Those were the dates. Not so important, really. Did they observe them? Did they predict them? Did they discover them? Well, the correct language is, again, they're talking about assumptions. They're making an assumption that they're dealing with particles here, and they're dealing with assumptions that they're dealing with something called a black hole, a star that collapsed on itself, and dark matter, that they're dealing with the assumption that there's mass, hidden mass in there. But all those assumptions are based on concepts. They're not based on physical objects. They're based on mathematical concepts, which they reify and treat as physical objects in the course of their explanation of the mechanism. That's what they're doing. And so there's no observation, there's no prediction, no discovery, right? Here it is again. This is what they're talking about. They're talking about assuming and explaining. They're making an assumption and they're giving you an explanation. But if they tell you that all these were assumptions, you would clean your nose holes with what they're saying. You say, oh, but they're assumptions. They're suppositions. The suppositron, it's a supposition. No, they had to say a little more. They had, look, we predicted it, and then we discovered it because here's a little trace, so please believe us. We have evidence, and here's the equation also that stands behind it. So what do we have today? Well, we have a real interesting world. Okay, let's get rid of this. These people are developing equations for inexistent stuff. They find all these dark things that they cannot picture because they're all dark, they're invisible, they're translucent. They can't see the black hole. They just say, what else could it be except a big mass right there in the center that's moving all the stars around or flaying them alive or whatever, right? And so this is what you're paying for. This is what they're developing these days, okay? They're developing equations for a dark unicorn. There you have the equation, okay? My equation, okay, by the way. I take credit for it, full credit, okay? So you can try to dissect it to see if you can understand it. It's the equation for a dark unicorn, okay? And if that doesn't do it, then you look for black leprechauns, okay? And there's the equation for black leprechauns. And this is what they're developing these days, okay? They're developing equations, especially in string theory, for inexistent stuff that has no bearing whatsoever on reality, has nothing at all to do with physics, okay? And so what can I tell you? That's what you're spending, or they're spending your tax dollars on. There's all this mathematical work, people like Ed Witten and Lenny Susskind, this is what they're developing. They're developing equations for inexistent stuff. And one of the questions you should ask yourself, here you have thousands of mathematical physicists. They're all in their offices every day, right? What do they do? Even assuming, let's just play devil's advocate here, that they're, developing, each person is developing one equation per week, right? New equation. They go through all their calculations, all their integrations and calculus and whatever, linear algebra, whatever they need, and they come up with an equation. One equation per week per mathematician. It took them the whole week. Hopefully they earned their paycheck at the end of the week saying, look, boss, here's the equation that I've been working on this whole week, right? You showed something for the time that you spent, right? So you come up with one equation. Multiply that times thousands of mathematicians in every country of the world. In their offices, they're all developing equations. One guy for black holes, the other guy for dark matter, who knows what else. So we should be, and that's, 52 weeks a year, right? Thousands of equations. Where are all these equations? What are they doing? What are they describing? We're done with equations. Now, whatever the equation comes out now is ridiculous. It's on irrelevant, inexistent stuff, for sure. What else can you develop as far as an equation? Is this the holy grail of mathematical physics? Just do equations, past equations, regurgitate them, and redo them, see if you can come up with a new equation? What are these people doing? How do they earn their money? And so that's a question for you to take tonight when you go to bed, okay? Think about it. We'll see you next